Hello. Welcome back to our discussion of computational physics. Today we'll add a new dimension to our discussion, and we'll talk about fractals, and we'll mix it with statistical physics. And this is an interesting topic, particularly relevant to computational physics, both because many of the models that we'll discuss can only be implemented with computation. So you couldn't do them otherwise, so the whole field is developed with computation. Another reason it's so interesting, particularly for those of us who are scientists, is that in some ways it's an area of mathematics, talking about dimension of objects. But as a scientist, it gives you a new way of looking at nature. It gives you a new way of looking not only at nature, but some of the simulations we develop, which model nature. And we discover they have a very simple underlying feature, much like these nonlinear systems we've already studied. But here the underlying feature will be the dimension, the mathematical dimension of the object and what it tells you about the object. And you can see that object in a new way, and you can also see beauty, or you can do the opposite. You can look at things that you think are beautiful and maybe understand why you do. So that's a lot for just a simple lecture. It'll be 2 lectures. But let's get on with it and see what we mean by fractals, see some examples. And in fact, this won't be very mathematical. It'll be almost all learning by examples, understanding by examples, and then analyzing some of those results. So look at the first slide. Okay, what is a fractal? Well, a fractal is an object that has fractional dimension. Okay, so fractional dimension is the main thing mathematically. And then you have to ask the question, what does it mean for an object to have fractional dimension? And I don't think people really knew this. You knew what it meant for an object to have dimension that's an integer, 1, 2, or 3, because that's the world in which we live. But to have fractional dimension, it wasn't clear. And interestingly enough, a lot of the work, a lot of the demonstrations came about by Benoit Mandelbrot, who was a mathematician at IBM Research in Yorktown Heights, at a time when I actually had a sabbatical there, trying to round out my computational skills, but we never worked together. And he's given credit to inventing the term fractal, meaning fractional dimensions. And so when we'll talk about fractals, we'll talk about 2 different kinds of fractals. And we'll give you an example even today. You'll see 2 of them. One kind has 1 dimension for the whole object, and that's its fractal dimension. The other kind is not the first kind, which was more geometrical, but rather more statistical, more stochastic, that has randomness built in. And then you can have a fractal dimension which only exists maybe on the average, may vary from object to object, but be about the same number, and which may vary as you move within the object, interestingly enough. So what we see here is we agree that all lines have dimension 1, all triangles that lie on a surface have dimension 2, and a cube has dimension 3. So then if we figure out some definition for a fractal that agrees with what we mean by a line, a triangle, and a cube, then if we apply it to some other object and we get some non-integer value, we have to accept that as a possible reasonable description of that object. Okay? So we'll talk about today in particular the Hausdorff dimension, as it's often called, d sub f. D for being dimension, f because it's a fractal. But note also here this beautiful figure. Now this figure here could be a fractal, it could be just random clustering of numbers, but then it's been given a little bit with Poivre, been given a little bit of fog and a little bit of height and texture, and it looks very much like what things up here in the Pacific Northwest look like. It looks like a coastal range, but this is just a very simple mathematical model that looks much like reality. So it's very interesting. Okay, so what do we mean by fractal dimension? So let's consider an object of uniform density, side L. L is just a length, it doesn't matter. Uniform density just to keep simple. Okay. Well, we know if we have a pencil, where's a pencil? Gone. Here's a pencil. Okay. We have a pencil, a linear object. As it gets longer and longer, its mass increases. So we'd say, okay, its mass depends on the length. Okay, that's right. And if we have a surface, two-dimensional object like this, its mass depends on its area. You make it wider and wider, the area increases linearly, and the mass increases proportionally to the area. Fine. Okay? So 1, 2, same with a cube. So this makes sense. The mass goes like the length of the object, the length of a side, times to the power d, which is the dimension. If we take the mass and say, okay, what about the density of the object? So essentially we take the mass divided by the area or the volume, whatever the case might be. So we have L to the df divided by L squared. We get that the density should vary like the length of a side to some power df minus 2, at least for these two-dimensional objects or an object in a plane. Okay? So this works for 1D, 2D, 3D objects. Let's see if we can apply it to other kinds of objects. So let's look at the next slide. So here we'll talk about a Serempitsky gasket. This is one of the classic examples of fractal. We'll look at both a statistical fractal here and a geometrical fractal. And this is a pattern we'll derive, deduce, calculate, that's been found on ancient monasteries, in the tiles of ancient monasteries. It's also a pattern which occurs in shellfish, on the shells of fish. Okay? They must both come from a very similar formula. So here we'll do it for yourself. So let's start off. Let's draw an equilateral triangle. Okay. So here, not bad. Now I got to get them together. Go up right there. Right there, I said. Okay. So that is an equilateral triangle. Okay. Okay. Let me tell you what we have to do. Okay, so I can draw it again. So here's our equilateral triangle. We'll do it again. Perfect. Okay. Now, we have to place a dot someplace within the triangle. Doesn't matter where. So I'll do it with my eyes closed. Tell me if I'm inside the triangle, Sally.
You're inside.
Okay, right there's our starting point. Okay. Fine. We'll label the vertices. Let's call this 1, 2, 3. Okay. Now we have to randomly pick a number, 1, 2, or 3. Pick a number.
I go with 3.
3. Okay. So we pick 3. If 3, then we draw a line from our point to 3, and then we put a new point right in the middle. Okay? So there's our new point. I'll make these points nice big blocks. Okay? Pick another random number.
Let's go 2.
2. So we draw a line here, and then we put a point in the middle. Another random number.
So 1.
1, okay. So we draw a line, not bad, and we put a point right in the middle, which is right about here. And already you can see the points sort of clumping together in this triangular form. One more, just to see. Okay, where am I here? So this is now another line to here, and I know you're impressed with my drawing ability, but, and there we go, okay? So if we repeat this again and again, here it's done for 10,000 points, you get a figure that looks like the one on the bottom here. And it's a very interesting figure. It obviously has triangular symmetry to it. You see triangles every place. And if you look close, put your nose on the screen, you'll see that it's just a bunch of dots. And we'll enlarge it later on. You can see that in detail. But you also see that this equilateral triangle appears every place again and again. Okay? And we're beginning to see that here. Here we have a triangle in the middle, in fact, which will grow up into a bigger triangle. And if you wanted to write an algorithm for this, we could just say the new points, x to the k plus 1, y to the k plus 1, is our previous point, plus an integer n, a random integer, 1, 2, or 3, divided by 2. Okay, and that's how you make it random integer. So this is the algorithm, and this produces this gasket. This is a fractal, as we'll see shortly in different ways. Very interesting. So let's look at the next one. Okay. Let's analyze this fractal and determine its fractal dimension. See if there is such a thing. So here's how we'll do it. Okay. So recall, we'll use the basic formula we've derived, deduced, suggested, hypothesized, that the density of an object is equal to some constant, which we don't care about, times the length of the side, this is a planar object, to the fractal dimension df minus 2. Okay? So here we have a triangle to start with at A, an equilateral triangle, and now we won't do this randomly. We'll make this a geometrical fractal. Has the same properties. It's just very easy to draw. And you can imagine each dot that we put in the previous one, or each tile, you can think of these as little tiles we'll be making, having a mass 1. So you can forget about the mass. And then that means that the density rho should be proportional to L to the df of minus 2, as expected. Okay? And so we have to figure out what the density is. Okay? So if that's true, if rho is proportional to L to the df minus 1, then the logarithm of rho, so if you made a plot of the logarithm of the density, should be linearly proportional to the log of L, and the proportionality constant is just the fractal dimension minus 2. So what this means is we'll look at this object, we'll construct a fractal, and we'll take the density of it for various values of L and make a plot, deduce, or take some numbers, deduce what the fractal dimension is. So here's how we make a fractal, a Sierpinski gasket, out of this triangle. So we start with the triangle here, and then we inscribe an inverted equilateral triangle in the middle. We get the figure here. Okay? So then we take the figure, and that's what we have below here. All this is shaded in. So we now take this figure, and then in each place we inscribe another inverted triangle here. Okay, so that's going to be the solid object. We make, again, we bisect each line of the triangle that exists, and that's now open, and that's now open. So we remove that, and then we get the figure at the bottom, and then we keep repeating that on and on, thousands or millions of times. And what you can see happening is where at first we had a solid triangle, we cut a hole in the middle, we keep cutting these holes, and the object gets more and more porous, more and more full of holes as we increase. Okay? So if we look now at what's actually happening, and we just say, what's the density each time? Well, after the first step, rho is 1, 2, 3, and there were 4 triangles up above, so the new density is 3/4 times the old density. That's obvious from A to B, and if we do that from B to C, you find the same thing. Okay, the density has decreased to 3/4 of what it was. Well, then that's all we need to know. So we know then that if we have our equation here, the log of rho is proportional to the log of the length. So df minus 2 is just the slope in the plot of log rho minus log L, or just the change in log rho divided by the change in log L. df, we just move the 2 over. If we actually use the numbers here, one side, the other's 3/4, that's the change in rho. The change in L goes from 1 to 2, because it's 1/2. And then we get the fractal dimension of our Sierpinski gasket is about 1.585. Interesting. What does that mean? Well, it's saying that this object here, this gasket we're producing, it has more, it's a greater dimension than a line, but it doesn't have as much dimension as just an ordinary triangle. And if you think of dimension as a measure of how an object fills space, then you'd say, oh, this gasket doesn't fill space quite as much as a triangle, but it fills it more than a line, 1.6. That's its fractal dimension. Very interesting. So we've produced a fractal, number 1. Number 2, we've used a very intuitive, but that's all we can have. Dimensions are just defined by the world in which we've grown up. So we've used an intuitive definition to get one measure of the dimension of this object, and it comes out to be fractional. But we've also seen how these kind of objects have this symmetry built in. They look very similar all the time. And that's this aspect mentioned at first. What's true for fractals is they all seem to have this self-similar property, that if you look at any one little piece, like this little piece down here in C, it's very similar to what it was at a different scale. So as you change the scale, make it, say, smaller and smaller, or make the scale higher and higher, look at smaller and smaller details, you see something that looks very similar, maybe not identical, but at least similar to what it was when it was larger. And so this demonstration took advantage of that rather, and used that to define and deduce the dimension. So let's get on and look at another fractal. Pretty, aren't they? These are not photographs. In fact, sometimes when I teach the class, I'll bring in a real fern, pass it around to the students. It looks just like this thing on the screen. And this is a tree. Okay? Well, plants and ferns particularly are often very beautiful. What does that mean? It means when we look at them, we consider them something of beauty. Why do we consider them something of beauty? Well, we like the shapes. We like the symmetry. There's a high degree of regularity and symmetry. Humans tend to like that. And yet, they're not perfectly regular and similar, and many of us like that too, like a little bit of randomness, a little disorder mixed in with the sort of geometrical perfectness. Okay? So, is it really possible to have an algorithm that describes something like a fern that's both random and simple at the same time? And the answer is yes. Okay? The key here is the self-similar aspect. The fact that if you magnify and look at any one little piece of the fern here, like one of these fronds, it looks very much like the fern itself, which is exactly what you see here. We'll see that in our simulation shortly. Okay? So, can this come from a simple algorithm with randomness? It's really a question. And the only proof is in the pudding. You have to do it. Then comes the somewhat philosophical question, which is, as we'll be able to do, if we can figure out a very simple algorithm that we can just throw on a computer and generate beautiful ferns, does that mean that nature, which generates beautiful ferns on its own, must be following some very simple law, some very simple algorithm? We can't answer that, and if you look in the biology, often there's details of how it goes on, but in the end, it obviously must be something similar, some similar laws being followed. Okay, so let's take a step back before we do some examples, give you some mathematics so that we get that over with, and then we can have some more fun. So let's look at this next slide. Okay, this next slide, we talk about self-affine connection. So this is sort of mathematical theory of these transformations, these statistical models we're developing for fractals. And what does affine mean? It's like, if you have a girlfriend or a boyfriend, you have some affinity for them. That means you're attracted to them. You like to be together. You like to relate to them, okay? Some closeness to them. Well, in fractals, when we speak of self-affine connections, we mean there's a relation as you go from point to point is called a self-affine connection. And because of this connection, there is self-similarity. So the cause of the self-similarity is the simple connection from one set of points to the other. Just like when we drew the triangle, we connected them always with some rule that led to the self-similarity. Okay? So we can think of the Serempitsky gasket, and this was the rule we followed. We took the new point, xy values to be the old point, divided by 2, plus some distance, the distance here to the vertex, also divided by 2. Okay? So in this case, there was a scaling factor, the factor that multiplies the old values of the points, and that was 1/2 here. And a and b, or a and b over 2, which doesn't matter, is a translation. So the new point is the old point scaled plus a translation. If the scaling factor is greater than 0, which it is in this case, excuse me, then that's called an amplification. I think that should be amplification. I think this should be a 1, and that should be a 1. Okay. but it's gone now, so we'll leave it at that. Now we'll make it a 1 again. Okay? So if the scaling factor is greater than 1, it expands the object. If the scaling factor is less than 1, it reduces it. Okay? So that's what we have, scaling here. So here, as you see, we have a scaling factor which is a half, and the triangles kept getting smaller and smaller each time we multiplied through. Okay. So this is the general scaling, x prime, some value x and y. We can also have a translation added in, as we have here for the Serum-Pinsky gasket. And the other possibilities is we can actually have a different relation for x's and y's than this, from each other. They don't have to be the same. And that gives you a rotation. Because when x prime equal to x cosine theta minus y sine theta, that's just a simple rotation in a plane. And likewise with y prime, with the obviously difference in sign here for a rotation. So that's the general form. Any of these forms, any of these combinations produce an affine connection, rotation, translations, amplification, scaling. Okay, so let's look at this on a real object. This is the firm. So take a break. Look at this. Okay. So look at this slide. And what we've added here, which you may not have seen before in some of these lectures, is we have an electronic version of our textbook. So here's our textbook, which if you haven't gone out and bought one, you should do that maybe today or tonight, the latest, on Amazon. Okay? So this is our textbook, and it has codes in Java within the book, Fortran and C versions in the back. And we also have an electronic version of this textbook being produced as we speak, available as we speak now, and that uses Python, which is another language, simple, similar to Java, a little easier to program. And we've taken here in the lecture this sort of picture of a python, or maybe a snake anyway, to indicate there's some codes available. So in this case, we have a code called Fern3D. So it produces a fern, and it gives you some three-dimensional degrees of freedom for it in Python. And this other symbol code means that, as it's indicating here, we have a sample of the code to look at. So let's run this code. And you can do that in the ebook. We'll see if it works here live. You never know what works. But to give you an example of a fern. So here it's running. Open, yes? So here's our fern. It just produced the fern for you. I'll enlarge it. So that's our beautiful fern, just made from numbers. And here, with the right mouse, this is the 3D aspect, I can actually look at the fern. That's the back side of the fern. This is the front, and there's light coming in from the left. Here I'm rotating it so you can see it all. And then if I do this right, I can also enlarge this. Doesn't seem to be enlarging. Okay. So this is our fern. It's our beautiful fern produced with the code Fern3D. If you actually wanted to look at the code, you can click on the other box in the book, and then you can see this is the code. Okay, just the usual advertising and stuff. But the code itself here, as you can see, is just some simple affine connections. It's just x's and y's being related to each other in some very simple way, and that's it. And then this is just the plotting. We're just plotting up spheres for each of those points. So let's look at the code. So this is the algorithm. So this, believe it or not, this simple set of linear equations produces the fern. Barnsley figured this out. And what it says to do here is take from the old point, n y sub n and x sub n, it produces the new point. And it uses first this formula here. Okay, so this is the the starting values, and this is now the new x and y values here. And it does this with a 2% probability. So 2% of the time it does that. 15% of the time it uses this relation, and if you notice there's a comma in here, 0.5 comma, so this is the x value, that's the y value. Okay, that's the x value, the y value, etc. does this with 13% of the time, and it does this transformation 70% of the time. Okay, so there's randomness here because it has different transformations, and there's nonlinearity, at least in an indirect way. The direct linearity, nonlinearity, you'd expect to arise from some higher power of x and y. You don't have that here, but the fact that it's not just always x and y with one formula, but with various formulas, leads to nonlinearity, which is necessary for this fractal aspect. Okay? So you just run this, you repeat it again and again, excuse me, and what you see is it won't be completely self-similar. There'll be different aspects of it. Some aspects will have different fractal dimensions. For example, the fronds will have a different fractal dimension than the stem itself. But if you look at the stem, you find that it's actually compressed fronds itself. Okay. How does one come up with a formula like this? I've asked that question, looked about many times, and I think people just work hard at them. You can play with it. You can diddle some of the numbers. Each time you diddle some of the numbers, you get a different answer. So let's go on now and say, okay, so this is the old x and y values on the right, some linear combination giving you the new, and then I have to do this with different probabilities. How do I pick numbers with different probabilities? Well, the answer is very easy. If you want to have something with 2% probability, you just choose a random number between 0 and 1. And then if the number is less than 0.02, which should only occur 2% of the time, then you say that gives me 2% probability. If the number, say, is between 0.02, which is taken, up to 0.17, that's a range of 0.15, that's 15% probability, etc. 13%, 70%. So if we combine those two rules together, and this is useful for programming, we get this rather complicated looking formula here, which is how we produce the Bardsley-Fern. That's the algorithm. So what you see is it looks complicated, but it's very easy to program. You just take this as the rule, as you saw, write down a few lines of code, and it produces that beautiful, Bardsley-Fern here. That's the code. Runs very fast, as you can see, and it's quite beautiful. Okay, so let's get on. Let's look at the next slide. The next slide talks about another algorithm, another program. This program is called Tree. In this case, there's a Python version, which we can run for you, and there's a Java version, C version as well, and Fortran. They're all very simple, and here there's another affine connection. So here the new points are the old point, 10% probability, simple relation, a little more complicated, again with 10% probability, and then third, fourth, fifth combination here. So there's a lot of combinations, and that produces a tree. And so if we look at the tree here, run it, yes. And you can see the tree being produced just by points. So we'll run that again, and notice how the tree is being produced with the points right in front of you as the algorithm runs. And if you look here with the enlarged view, you can see, oh, it's just a lot of dots, isn't it? Yes, but each part of this tree, if you look at it, is similar in some ways to the rest of the tree. And if you analyze the fractal dimension of this tree, you'd see that it had a well-defined fractal dimension in each part, which is part of what gives it the regularity we like so well. So this is now a good time for a break, because we're going to go into more of these algorithms. But let's summarize what we've done. We've come up with a definition of fractal dimension, okay, of dimension which works for 1, 2, and 3-dimensional objects in the intuitive way. And then we've said, okay, let's apply this to some weird objects known as fractals, and we come up with fractional numbers. And then we looked at these weird objects and we said, they're not quite as weird as we thought. They always have a certain relation from the old to the new, the self-affine connection. And when you apply that, you always get a self-similar object, an object that looks the same as we look at it in more and more detail. So, take a break now. Go and try. Run the code. Play with the codes if you want. Look at the plants. Look at the fern. Modify those numbers and see what happens. Then we'll be back and we'll look at this in some more detail. See you soon.